So 6.1a slope fields. Hopefully you got it up on your screen for you. All right, so we need somebody to read about slope fields. Doug's going to read for us the yellow part.
Many times, differential equations are not explicit functions of a single variable, and sometimes they are not even solvable by analytic methods. Fear not, there's a way to graphically solve such and any differential equation.
All right, keep reading the blue.
A slope field is a graphical general solution to a differential equation.
All right, so have you ever watched the Weather Channel and seen like the vector arrows for like wind or high pressure, low pressure systems or whatnot?
Yes.
Everybody seen those? Okay, that's like a vector field or a slope field. And that's probably the most common slope field that you've probably seen already before. All right, and we're going to start using these. There are other applications, but that's probably the one you've mostly seen. Yeah. All right. All right, so here we go. We got dy dx is equal to x squared. This one is in explicit form. However, it doesn't always have to be. I will be talking about the nuances of these, but we're going to start out easy. So we need to find the slope field of this differential. Well, let's substitute in. All right, so if I substitute in negative 2, 2, what's my slope? 4. If I substitute in negative 1, 2, what's my slope? 1. If I substitute in 0, 2, what's my slope? 0. If I substitute in 1, 2, what is my slope? 1. If I substitute in 2, 2, I get 4. Will my y value change anything here? No. So it's going to be 4 all the way down here, and then it's going to be 1s all the way down through there, and it's going to be 0s all the way down through there, and so forth. My y's aren't actually changing anything because this is actually an explicit form. So now we need to start drawing the slope field. And you don't have to be extremely accurate. However, there will be a little bit of accuracy needed here. All right, what does a zero slope look like? Just straight horizontal, right? All right, so at 0, 2, I always like to start out with my zero slopes. So we were just straight across right there. See how we did that? All right, so I'm just going to go straight across, just like that. So I have my zero slopes, all 5 of those points. Pretty easy. Now I like to start out with my 1 slopes. They're kind of a little bit particular about 1 slopes sometimes. So if I have a slope of 1 right there, I kind of look right there when I draw my line. You see what I'm saying? And so my 1 slopes, we just kind of go like that. All right? A slope of 1. Yeah, if you were to continue it, it hit that little spot. Exactly. All right. So those are all the 1 slopes. All right. And then we need to find our 4 slopes. Now, this is where you don't have to be extremely accurate. However, if you wanted to try to be accurate, if you're going here, you should actually be looking right there. Does that make sense? All right. However, just make it super slopey. All right. Pure mathematical term, super slopey. All right. All right. So anyway, we're making those a positive super slopiness. See how that worked? All right, cool. So there is our completed slope field. Now, I want to talk about a particular solution if I were to add it. I'm going to add on to this problem. So I'm going to say y of 0 is equal to, let's say, 0.5. All right, so I'm going to say y of 0 is equal to 0.5, just because. So where's that initial condition starting? At 0.5. And so I'm starting out right here. Does everybody agree with that? Now, if this were to move to the right, which way is the slope field pushing my line. So if I were to start out going to the right, if I were to start out going that way, which way would it be going? Would it be going up? Would it be going down? Would it be going straight across? What would it be doing? It'd be going up. It'd kind of do something like that. See how that works? All right. And if it were to move left, what would it start to do? It would start to go down. All right. So it would be kind of doing something like that. So everybody see how it kind of got pushed by those slopes or on that slope field. All right. It's just kind of going with the flow. That's the way I think about it. Does that make sense? Now, one thing that I have somebody do like almost every single year.
Wait, I know it.
I sometimes have students that try to go to the right and then they're like that. Okay? I don't know exactly how to explain it other than that broke the slope field. Does that make sense? If it's going to the right, it's being pushed up. Do you see how all those slopes are pushing it up and it can't go perpendicular to them? Does that make sense? Okay, so don't do that. However, you don't have to be extremely, extremely accurate. Now, I do want to entertain what Joseph was just talking about. This is in explicit form. So if I were to actually solve for y, what would it be? Y equals what? X cubed over 3. All right, and then plus c, and my c is actually going to be 0.5 here. So what does this blue line look like? It looks like an x cubed function. Exactly. All right. So that's kind of the way they relate a little bit. However, equations are really cool because they don't have to be in explicit form. All right. And the next two examples are not actually going to be in explicit form. All right. So let's look at this one. So now we have y prime is equal to x plus y, and I have this initial condition again. So let's build a table. At first, this is the way we really need to do it to get in practice of it. So if we substitute in negative 2, 2, what do we get? 0. Substitute in negative 1, 2, 1. And then if we substitute in 0, 2, we get? And then? All right. And then if we substitute in negative 2, 1, what do we get? Negative 1, and then 0, and then 1, and then. All right, we substitute in negative 2, 0, we get? Negative 2, and then. All right. And then our next line, what would we have? Negative 3, then. Negative 2, then. Negative 1, then. 0, then 1. And then if we substitute in negative 2, we end up with negative 4, then. All right, fantastic. So now we need to actually sketch the slope field. All right. So I always like to start out with my 0 slopes. So we're going to sketch our 0 slopes just like so. All right. So all of those have horizontal 0 slopes. All right. So now let's either work with this portion or this portion. All right. Which one do you want to work with first, the positives or the negatives? Let's work with the positives. All right. So now we have slopes of 1. So we need to be very accurate on our slopes of 1. All right, so we have slopes of 1 going on there. And then slopes of 2. It's a little bit more slopey than 1. So when I'm looking at 2, if I'm looking at doing the slope of 2 here, I'm kind of going right there. You follow me? All right, and then more slopes of 2. And then slopes of 3. And then slopes of 4, which is super slopey. All right. See how we created that slope field. All right. And then on the next portion, so now we're doing the negatives. So negative 1, those need to be pretty accurate. So we have slopes of negative 1. And then we have slopes of -2. So if I'm going at that portion right here, I'm really looking right there. Okay, so we have portions of -2. And then -3. And then super slopey -4. So now we're going to utilize this initial condition, and it says y of 0 is equal to 1. So we start out at what?
1. I
0, 0, 1. So when it's moving to the right, what is it doing? It's moving to the right. What's it doing? It's going to go up just like that. All right. Now, I sometimes have questions on like, well, Mr. Flick, can you do that? Or does it go like that? I'd say either. Okay. It just can't do that. You following me?
Yes.
All right. But if you're saying like, is it there or there? Either one's good. Does that make sense? All right. So it's just kind of a general idea of what it is. Now, as it moves left, what's it doing at the get-go when it's moving left? It's going down a little bit, and then what? Then it gets horizontal, and then what? Okay, it's moving here, and then it goes horizontal. Then what? Then it starts going up. So it's actually doing something like that. All right. I had somebody last class say it went down as well. This right here is a horizontal slope, which means this is going to be straight right there. Okay? If this were a vertical slope, if this were like that, then it might be able to go down. Does that make sense? All right? But it's horizontal, so it's leveling off, and then it gets pushed back up. Okay? Does that make sense? All right. Do what? On this one, I want to go into what we might be going over soon. All right, on the next page, we're going to go over something. I want to find the zero slopes of this differential. So this y prime is another way to say dy dx. All right, so I want to figure out when my slopes are 0. So if I have 0 equals x plus y, usually my lines are in terms of y. So what would y equal? -x, right? And so a line, y equals -x, is this line right here. All right? It's that line right there. And guess what's happening on that line right there? I have all what? Zero slopes. You see how that worked? All right, so if I had to actually see where those were, that would be a good way of looking at it. Leads us into this one. So we're going to match the slope fields with their differential equation. All right. My first year teaching this, I said, just pick some numbers, see which one matches up. It's a terrible way to teach it, honestly. I didn't know what I was doing. All right. But since then, I found out better methods. All right. So we always like to look for when dy dx is 0 or 1 a lot of the times, and then we look for quadrants, and you'll see what I mean after we go over this example. So on part A, I got dy dx is equal to e to the x. All right, we're going to leave that guy alone for right now, because is e to the x ever going to be 0? Never. All right, so we're going to leave that guy alone for a sec. Let's look at number 2. I'm going to set dy dx equal to 0 on this one. So I'm going to say 0 is equal to x over y. So I multiply by y, x is equal to 0. So I should have 0 slopes at the line x equals 0. X equals 0 is another name for what? The y-axis. So does A have 0 slopes the whole time on the y-axis? No. How about B? It does, so it could be B. How about C? Does it have 0 slopes on C? Yes, it does. This levels out. You see how it's leveling out? Every single time. All right. So C actually does have 0 slopes on that axis. All right, let's look at D. Does D have it? Yeah. Yes. Does E have it? No. Does F have it? No. All right, so we're in between B, C, and D on that one right now. We're going to keep moving. So let's look at number 3. So we're going to set dy dx equal to 0 again. So I got 0 equals 2 minus y. What does y equal? 2. So I should have horizontal slopes. I should have 0 slopes on the line y equals 2. Which one tells me that? A. A tells me that. Oh, not A there, silly. A right there. All right. So we figured out what A is. All right. Let's look at number 4. I have dy dx is equal to x. So if I set dy dx equal to 0, I'd get x is equal to 0. Well, again, what are those in between right now? B, C, and D. All right, let's look at number 4. So now I have dy dx is equal to x minus y. Let's set dy dx equal to 0. So I get 0 is equal to x minus y. What does y equal? X. So I have a line y equals x. I should have 0 slopes on all of those. Which one tells me that? E. E has y equals x. I have 0 slopes on that line right there. All right, pretty cool how we went through that. All right, let's look at number 6. All right, so now I have dy dx is equal to sine x. It's a nice trig function. Which one is the only one that looks like a sine or cosine curve? D. All right, that's literally how I will explain that one. Okay, do what?
It's going up and down.
Yeah, it's the sine wave. All right, it's the cosine wave. All right, that's exactly all I need for that one. Let's look at part A again. So, or number 1. So dy dx is equal to e to the x. What do you know about e to the x? It's an exponential function. All right, and so what does e to the x look like? Just goes whoop, right like that. So which one does that? F. F does that. All right, so I will never have a horizontal slope, and it's going to get pretty steep at the end. So F does that. Now I'm in between B and C for 2 and 4. All right, so this is where we need to look for commonalities. All right, what do you notice about the slopes in B? What do you notice about the slopes in B? What? They're decreasing. Okay, they're negative then positive. I like that. All right, so let's just talk about these positives. All right. So dy dx is positive when? dy dx is greater than 0 when? When x is greater than 0. Does it have to do with y? It doesn't have to do with y, does it? So let's look at number 2. dy dx is x over y in number 2. If I substitute in a positive x value in any y value I want, what do I need to get? I need to get a positive, right? Can I do that on number 2? No, because I substitute in a positive x, but what could y be? Negative. What will that result make me? That would make my result negative. Well, let's make sure number 4 is okay with it. If I substitute in a positive x and anything for y, will I get a positive? Yeah. Yes, because it's only dependent upon x. So guess what number 4 is? That one has to be B. Do you see the thought process on how we went through that? All right, let's look at C. I want to prove this one to you. Do we see any commonalities in letter C? When's dy dx positive? Let's just do positive. First quadrant. What's happening in the first quadrant? X is what? Greater than 0, and y is greater than 0. All right? Both of them have to be greater than 0, or if we're talking about the third quadrant, this is always positive too, right? dy dx is always positive there. And that means x is what? Less than 0, and what? Y is less than 0. So both of those things have to occur. Well, if I substitute in a positive x and a positive y, no matter what those positives are, am I going to get a positive? How about a negative and a negative? Will it always be a positive? Yes. All right. If you look in quadrant 4, that'd be x is positive and y is negative. That should always be what? Negative. Will that work too? All right. So number 2 is C. Do we see how we went through that?
Ha ha, very funny.
Thanks. All right, let's look at this one now. So I have this differential. I have xy over 2 is equal to my slope dy dx. I'm going to make a slope field, and then I'm going to do a tangent line. All right. What did they not provide me? A chart. So guess what we're going to make? A little chart. At this point in time, I think charts are useful. Once you do these a decent amount, I think you can actually do them without. But right now, we're using a little chart. All right. Let's substitute in negative 2, 2. What do we get? Negative 2. How about negative 1, 2? Negative 1. How about 0, 2? 0. Anytime we substitute in 0, what's it going to be? 0. All right, so when I see that kind of stuff happening, I'm going to fill out those zeros real quick. You following me? All right, that's just the way I kind of like to do it. And then let's complete our chart some more. So if I substitute in 1, 2, I get 1. If I substitute in 2, 2, I get. If I substitute in 3, 2, I get 3. All right, so now if I substitute in negative 2, 1, what do I get? Negative 1. If I substitute in negative 1, 1, what do I get? Negative 1/2. If I substitute in 1, 1, what do I get? 1/2. If I substitute in 2, 1, I get 1. If I substitute in 3, 1, I get 3/2. All right. And then if I substitute in negative 2, negative 1, I get. And then if I substitute in negative 1, I get 1/2. If I substitute in 1, negative 1, I get negative 1/2. Then negative 1, and then negative 3/2. All right. So now when we start completing our little slope field, I always like to start out with 0 slopes and just knock those out right here. So then I got my 0 slopes. Right there. All right. And then on these kind of problems, I kind of like to work with quadrants at a time. All right. So I'm going to start with my top left quadrant, my second quadrant, and kind of knock those out. I like to start out with the negative 1s to make sure that I get those right. And then my negative 2s are going to be more slopey. My negative 1/2 is going to be less slopey. See how I kind of worked through that one? That's just the way I like to do them. All right. And then if I'm going to complete my left side, so let's do quadrant 3, I need to make sure my 1 is correct, and then 1/2 is less slopey than that. See how I did that? Am I taking all the time in the world to get those exactly right? I'm not, okay? I don't need you to. All right, your 1s and 0s have to be pretty accurate, and then your other ones just kind of need to be more or less slopey than those, okay? All right, so then let's work with the first quadrant. So my 1 slopes look pretty good. My 2 slope is more slopey. 1/2 is less slopey. And then we get slopes. All right. See how that one worked. All right, and then if I do my fourth quadrant, I'm going to do my negative 1 first, and then go from there. All right, pretty good. Usually slope fields on an AP exam is worth 2 points. A lot of the times it's either like your 0 slopes and 1 slopes is worth a point, and then the others are like worth the other point. Okay? All right. All right, let's look at part B, and I need a reader. Thanks, Harshna.
Let f be the function that satisfies the given differential equation. Write an equation for the tangent line to the curve y equals f of x through the point 1, 1.
All right, fantastic. So, what do I need for a tangent line? A point and a slope. What'd they give me? They gave me a point. What do I need to find? A slope. Well, they gave me a slope equation at the beginning, so let's do it. So now I find dy dx at what? 1, 1. Why do I need to see 1, 1 on that and not just x equals 1? Because I have y in my equation of my slope. All right, I need both x and y on that one. So dy dx at 1, 1 is 1/2. All right, so I need to see that you showed it with correct notation. Thanks to Leibniz, we just found out. All right, so I have a point, I have a slope. Now let's write an equation of my tangent line. So y is equal to 1 plus 1/2 times x minus 1. All right, hopefully we can build that pretty well. And then what is it asking me to do? Use that to estimate the value of that. I need to start with this good notation here. So I want to find f of 1.2, and I'm going to say it's about equal to. It's an estimate, so I need about equal to. I need my squigglies. All right. So now we just substitute in 1.2. So now we have 1 plus 1/2 times 1.2 minus 1. So 1.2 minus 1 is 0.2. 0.2 divided by 2 is 0.1. We add it to 1, we get 1.1. All right, so f of 1.2 is about 1.1. Pretty good? Hi there.
Do you have to say let y equal f of x?
No, I don't have to say that at all because it gives me right there. They defined it. All right, good question though. You have a slope field worksheet. On the slope fields, you have 6 slope fields on the worksheet. I just need you to do the odds. All right, so 1, 3, and 5 are the ones you need.